Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
My friend from high school, Louie, and I, whenever we saw a sequel, we would always say it's Saturday Morning Physics 2, The Beckoning, or something like that. But in this case, it's actually what we're gonna do today. We're gonna think about, I guess, a tour of homes instead. It's not. At first, it doesn't sound so tantalizing, but trust me, we'll get there. To remind you, the beginning question that we had last week was, what are the applications of cosmology? And this question was, well, it was actually posed by my grandma several years ago, who thought that we were sort of wasting time going into space. But it was also posed by my girlfriend when she thinks that she doesn't think my work is useless, but she likes to give me a hard time. So I like to take the next step in that discussion, and hopefully by the end I'll have given you my answer, and you may have come up with some of your own. But let's start with our putative home, Earth. So this place is something we know and love. This is a NASA composite illustration from what we know from the inside. And it's about 12,000 kilometers in diameter. That's its size. So you might want to look for these numbers as we go along. They help you keep a sense of scale. As we zoom out, we come to one of my most cherished pictures. This is from the NASA Lunar Orbiter 1. This picture was taken on August 23rd, 1966, and this is literally, quite literally, the first time that we saw ourselves. Right now, we're about 375,000 kilometers from Earth. If we look at our solar system from a different vantage point, you'll see us here. And if we zoom out just a little bit further, you'll come to another image that you might be familiar with, the pale blue dot that was popularized in one of Carl Sagan's books. And though he is inimitable, I love his voice. It's amazing. He has this really deep drawl. This image was taken in 1990 by the Voyager 1 spacecraft as it reached the edge of our solar system. And now we are about 6 billion kilometers for those who are counting. And this means you could fit about 1 million or 1 billion, what did I say? 1 million Earths from end to end. Oh, someone's doing math over there, that's good. Okay. And so if we zoom out, we get to what I think of as our home. And maybe that's because I'm an extragalactic researcher. Maybe it's because I think of really big things. But this is how I see our home, the Milky Way. And now we're about 400 quadrillion, yes, 400 quadrillion kilometers in size. But we can just say it's 12 kiloparsecs. So we'll change numbers now. And parsec is a new unit of measurement that we'll use. But our galaxy actually lives in an even larger place. Scale here is about whatever that is, kiloparsecs. It's very large, but it's still a fraction of the size of the observable universe. And if we think of that as our neighborhood, as a community or a town, then I like to think of our galaxy as a home, as a house. And now the next part, in the next 20, 30, 40 minutes, I'd like to talk about what it goes into making this thing come together. What are the pieces that make this stand and function properly? Okay, let's dive in. So the periodic table that you know and love makes up the gas and stars, the things that we can actually see. This is the same stuff that we're made of. And in the early universe, it was mostly just hydrogen and helium, because nothing had grown to spew out more complicated elements. And this gas and the stars that are made of it, they are bound by gravity, but they also feel other forces like electricity and magnetism. And fusion is what allows stars to form, and what gives us the light from the stars. So as gravity pulls the cold gas of the interstellar medium together, the hydrogens fuse, and from that they give off light. And the kinds of stars that we can get from this are very coarsely two kinds of stars. The younger, hotter stars, which are blue, and the cooler, older stars, which are red. And the star's mass, this is something you might want to keep in mind for the next few minutes, next 10 minutes or so. The star's mass determines its fate. And this is important in the evolution of a galaxy. So the more massive a star, the more likely it is, or there is a threshold beyond which a star can become a supernova and then a black hole. Below that, it's something that will just wither and live for quite a long time, like a white dwarf. So this is the stuff that we can see. Okay? So gas, helium, and hydrogen form into stars, which give us the light in our galaxies. And the forces at work here are gravity and electricity and magnetism. And then there's dark matter. I didn't miss anything on the slide. This is actually what it looks like. So eventually, hopefully, the Large Hadron Collider in Europe will, or actually astrophysical experiments may have a better chance, but hopefully within the next 10 years we'll have a better idea of what dark matter is actually made of. But as far as we know right now, the only thing that matters for dark matter is gravity. And how do we know that dark matter exists? Well, here's a quick bit of evidence for you. If you were to look at the rotation of our galaxy, the stars in the outskirts are rotating far too fast to not fly away if there weren't mass out there. So this is what you're seeing here are rotation curves for the galaxy. So this is the rotation as a function of distance outside the galaxy or away from the center. And what we would calculate without dark matter is this red line here, but this is what you measure in reality. So we need to include dark matter to account for that rotational velocity. So now that we see that the total content is dark matter in this gas and stars, which are broadly called baryons. So just quick review, dark matter, only gravity. It's the frame that holds everything together because there's so much more of it. 83% of the matter in the universe is actually dark matter, whereas only 17% is the stuff that makes up you and I. And the forces are the wiring and plumbing that hold everything together. And the light and heat are the way you know someone is home are the stars. And if you want a whole talk about just our galaxy and dark matter, see Oleg Naden's talk from 2009. Okay, now let's see how this thing is put together. Let's actually go through the steps. We have a fairly simple recipe for Galaxy Formation 101. It starts with, if you remember from last time, it starts with a cold gas cloud, and it has to be cold so that it actually can condense with the gravity. If things are moving around too fast, then gravity can't pull things down together. And just to remind you how that's possible, randomly distributed clumps of matter live in an unstable equilibrium, like a ball on top of a hill. Gravity pulls things down, and as space expands, the objects gravitate toward one another. And for a review of how this happens in detail, you can also see Gus Everard's talk from 2008. So the gas cloud collapses, stars form during that collapse process. And also very importantly, the cloud rotates and conserves angular momentum. And what do I mean by this? So the gas and the clouds are not just moving toward the center. They're not just moving radially inward. They also have some non-zero rotational velocity, some net rotational velocity. And just like an ice skater, as they are, I guess I'll do the twirl, as they pull their arms in, they have to move faster. So that's not the best example, so I'll show you another one. So watch the edges here. So we didn't form the spiral arms, but you saw that the the weights flattened out into the plane. And this is what happens as a spiral galaxy forms. It has to conserve momentum. So think Brian is an ice skater and that big, awesome Hoberman sphere, if you want to remember that. Okay. And then there's stellar evolution and death. So this is a key process because, let's see, I think whatever the talk ends minus 10 minutes, this will be very important. Actually, sorry, I'm not a harbinger of doom here. That's not the end of it's not the end of the galaxy. But as I said earlier, depending on the mass of the star, the protostellar cloud will either give you a black hole, a neutron star, or something like a white dwarf. And actually, so the demo lab folks came up with a really great experiment, and I'm going to see if I can do this for you. Who wants to make a galaxy right now? Anybody? Does this sound good? So let's put on the trusty goggles. There's a little black light. Okay, so let's spin this guy up. This water is spinning, giving us I mean, the analogy here is not strict, so don't take it away that way. But we'll see something fun. So this is just water in a cup, and oh, there we go. Nice. All right. Oop. All right. Oh, yeah, you can still see it, right? Okay. One more time. Spin it. Oh, so actually, this is an important point. So what you see here is that the gas is winding around, and it's actually, that winding thing is really important because that's not what happens for us, thankfully. So we live in the outskirts of our galaxy, actually. And the spirals that you saw there as it was spinning, they wound around and eventually collapsed back on the center. If that happened to us, that would be a big problem. So that tells us that the spiral arms of our galaxy are not formed through this spinning, through this winding, but they're actually, the best idea out right now is that it's density waves. The density waves are running around the edge of our galaxy. And a density wave is basically what I'm throwing at you right now. So I'm compressing and rarefacting the air with my voice. All right. So we've seen the process. We've recreated the process here. That worked out really well. And now let's see the most advanced simulation that NASA has been able to put together. This took over 9 months of continuous computation on a supercomputer. And it involves all of the physics, the state-of-the-art physics from star formation to UV background. And you can see the gravity is allowing clumps from outside to stream in toward the center, and you can see the spiral arms forming. And I'm not sure if they precisely set out to do this, but they're actually able to recover the significant parameters of our galaxy to at least within 50% for all of them. So I'm talking about size, mass, amount of luminous matter. So this is the Eris simulation. And the other videos on their website are beautiful. I highly recommend. So great. We've seen that galaxies form through the gravitational agglomeration of large regions of matter. And this affords a cycle of stellar birth and death. That's our first takeaway today. And what does this result in? This gives us basically two kinds of galaxies. So we have ellipticals and spirals, and I'll talk about how we get those two different things, the two different kinds in a minute. Hubble thought that the reason he made the tuning fork look like this is Edwin Hubble back in the 1920s, is that he thought that ellipticals could turn into spirals, but it's usually the other way around, actually. And for those of you who, thank you so much for coming so early on, not just a Saturday morning, but St. Patrick's Day Saturday morning. Those of you who came up so early, if you need a translation, this is for you. And if anybody wants to buy me an elliptical later, I'd happily. So the question of what kind of galaxy we get or what kind of galaxy we become is really a question of nature versus nurture. And these are actually very, very connected things in the case of cosmology and galaxy formation. But essentially what I'm trying to say is that it takes a village. Okay? And depending on, so if you're in the rural farmland, if you're a field galaxy, you're out in the middle of nowhere. Okay, you basically have only a few neighbors around you, and this means that you're not going to be disrupted with people asking you for sugar and things like that. And you only experience a few disruptions during your lifetime. And what this means for the color and the content of a galaxy is that it has more freedom to form new stars, because the cold gas will not have been disrupted, and it can collapse and form stars. And so it'll be bluer because it's forming new stars all the time, those younger stars. And we already talked about that key feature of the spiral arms and the density waves. If you are a city slicker, then you are going to have to deal with a lot of neighbors, a lot of racket, and you'll experience multiple disruptions, which means that you will lose your ability to form stars, and you'll become redder, and as we say, redder and deader. So this continuous movement, this heating, will remove the ability to form stars, and the galaxies will lose their spiral arms, and we'll see how that can happen right now. So there are two options in general to form an elliptical. One is, no, we're good, okay. One is harassment of a cluster, by a cluster core, or a large nearby cluster of a spiral galaxy. So let's see that. So we've zoomed, we're in an outer view, and we see the spiral galaxy pulled around and the tidal tails created just by running around the gravitational potential. The yellow is the spiral galaxy, of course. And we're going to zoom in and see the same thing happen, but in more detail. So if you watch the center compared to the outskirts, you'll see the loss of the spiral arms. The other option is through the ablation by the hot gas as a galaxy enters a cluster. So the blue is the incoming galaxy, the white is the edge, the putative edge of a cluster. As it comes in, you can see on the right, you can see the spiral arms are whisked away by the hot gas of the intercluster medium. And all you have left is this dense nub, which will contain the old stars that are redder and will remain redder forever. So we've thought about, we've looked at galaxies evolving in their different environments, and I study galaxy clusters, and I think they're awesome for one reason, because they contain most of the galaxies in the universe. And if galaxies contain the mass in our universe, then that means that we can measure the mass of the universe as a whole. And this is what I was talking about last week. If we're trying to understand this tug of war between the expansion rate and the matter in the universe, then we're going to need to understand both sides of them at least independently. But measuring the mass in clusters gives us that measurement. Also, so this is the Coma cluster, and if anyone knows their history back about 80 years, they remember that Fritz Zwicky in the 1930s was one of the first to postulate that dark matter existed, for a very similar reason to what Vera Rubin did with the galaxies earlier or later in the century. Basically, the galaxies are running around too fast to not be held in by some kind of dark matter potential. He was a hard character to get along with. I don't know if you guys have heard this little story, but he thought that everybody was they're spherical because they were no matter how you looked at them. But I think it was really the other way around. He was the hard guy to get along with. So let's think about a little bit of cosmology physics here, or a little bit of, this is closer to what I do on a daily basis. I try to understand plots like this, okay? So what we're looking at here is the counts of clusters of a given mass. So on the horizontal axis, you'll see mass, and this is measured in solar masses. So the largest number that you'll see there is 10 to the 15 solar masses. That's that would give us one of the largest clusters in our universe. On the left is still a very massive thing. It's 10 to the 14 solar masses, so only a order of magnitude lower. And then on the vertical axis, these are the counts in each of those mass bins. And now what I actually want to draw your attention to is the shape of the curve. So the black line and red line are just different points in time in our universe. So the red line is earlier, there were fewer things. Black line is later, there are more things. But the shape of the curve is such that there are clearly fewer larger things than there are smaller things. Right? And this is important for understanding the total matter density in the universe. That shape is very important. But in general, big things are rarer. Okay. So if you were to go look at our census data for the last 40 years, you could do a similar thing with populations in cities, and this is what I did. So I asked, what's the number of cities with a given population? Pretty straightforward, and as you'd expect, there are fewer cities that are larger. And you can see this in maps of the night sky that NASA has given us over the last 10 years. This is just great. And if you're a big fan of, I'll say if you're loving it, then this will be, this is another reference. So this is an artist's work where he actually measured the distance to the nearest McDonald's. And so it's the density of cities. So we're covered, I guess. So what kind of neighborhood do we live in? We've seen that bigger things are rare. There are fewer big things. But what is our local neighborhood has only a few galaxies in it that are worth counting. Oh, yeah, sorry, Triangulum. But if clusters are neighborhoods, then our local group is basically a suburb. And if we wanted to see where we sit on this curve as a suburb, you'd have to go way, 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 way to the left. So we're actually somewhere around 10 to the 12 solar masses. We're really small. So maybe there's no place like home, but it's actually quite average. So what we've seen in the last little bit is that red and blue galaxies live in very different environments, and it's crucial. It's crucial, the location, what's at that location. So if you remember Oscar Wilde, this will ring a bell. So what is the importance of simulations? Now, I haven't read this paper all the way through, but this is one of my favorite papers, and I just found a quote from this guy. I might read a little bit of it. But so Eric Holmberg is a character back in 1941 who took light bulbs and he configured them so that they were in the shape of approaching spiral galaxies. Okay. That's what these two things here on the right are. This is one spiral galaxy, this is another, and he gave them a slight rotation. Okay. So he had lights here, and he had photometers at all the other galaxies that he wanted to measure their distance away from. Because the strength of gravity decreases the same as the flux from light. So it's this 1/r² law. So he could substitute the flux of the light for the force of gravity and figure out a way to move these little light bulbs around and do the first simulation, which was analog. I don't know, that's just amazing. I would love to, well, no, I wouldn't love to do that, but that's pretty cool. So let me read you part of his quote, just because I think it's funny. In the early days, we usually had to work on a very small budget. We certainly were very poor. In the 1941 paper, for instance, I had to do all the work in person, including the rebuilding of the laboratory room, and making all the electrical installations. It was time-consuming, but gave some additional spices and satisfaction when you found that you could handle everything yourself. The scientist today is certainly a rather spoiled person, especially in the rich countries. I don't know. Something to think about. And I'm going to show you a video next, and I want you to look for these tidal tails. So we saw the tidal tail as the galaxy that was coming into the cluster was almost destroyed as it had spiral arms ripped off. We saw the tidal tail there, and you're going to see next that Holmberg actually did a really good job compared to modern simulations. So this is a simulation from Max Planck Institute in Germany. Two spirals coming at each other at different angles, but more or less head on. And there we go. So Holmberg was on his game, definitely. So this took over millions of particles, whereas Holmberg had hundreds. So again, you can see that the collision of galaxies also gives us, collision of spirals can also give us a nice elliptical. My question to you is, what do these 6 people have in common? I'm hearing what I wanted to hear. Yes, disruptive elements. These are people who challenge the system. They pointed out to us that a few things aren't exactly working as you intended. In other words, you could say mavericks, I guess, but maybe that doesn't give them enough credit. What I want to talk about now is what it takes to utterly alter the composition of large-scale structure from a very small element. And so what you're going to see next is the video of a black hole and its accretion disk spewing out not superluminal, but very, very fast particles and radio jets from its center. So what's happening here is that a black hole is formed from a very massive, dense star, and the accretion disk has torn baryons, has torn gas from other objects, and it's accreted onto this disk, and during the accretion, during the gravitational pull, the particles are being ejected, and they're giving off electromagnetic radiation. It's at the center. So the black hole is still very, very small within that. And the green jets coming out are radio jets. This is just pulses of radio light coming out of the plane. Remember that this is one of a billion stars inside a galaxy that's doing this. Not all the stars. My mom looked over at me like she was worried. Not all the stars in the galaxy are doing this at the same time, but one of them will. It's not common knowledge, but it's thought now that most galaxies have a supermassive black hole at the center. And so now let's see how this one star out of a billion, on the scale of less than a fraction of a parsec, can disrupt the environment that is millions of parsecs. That's millions of light years in scale. So there's the rotating black hole, the rotating accretion disk, the light coming out of the galaxy, this one galaxy, say in a cluster that has 100 galaxies in it. And it's ejecting these huge bubbles. It's creating bubbles within the intercluster plasma because the ejection of the fluid is pushing it away, is pushing away those cavities. Now, we thought we might also be able to make an AGN. This is called an active galactic nucleus because it's the nucleus of a galaxy. So we thought maybe we could make one of these here. Do not try this at home. I've always wanted to say that. So here's put some flammable liquid in here. We got to coat the bottom. What's that? So if you want a really good example of a disruptive element, our friend is back today. Is it going to happen? Oh. Actually, that's pretty awesome. I was not expecting that. sweet. Okay. Just move that. So what we see is that on a very small scale, we've been able to disrupt the, oh, it's still going. Yes! All right. On a very small scale, this little bit of fire has been able to disrupt all of the environment in between, and even pop a balloon. Okay. And just so you know that this actually happens in real life, here's a picture of a galaxy cluster, MS0735.6 plus 7421. These are in red is a radio view of the jets that are coming out of the central active galactic nucleus. That's just pretty awesome. And the thing is also is that we know very little about these objects. They're getting better classified every year, but we don't even know. It's hard to know. It's hard to predict when one of these things will happen inside a cluster. We just need more data, basically. So, quick reminder: the forces at work are. The forces at work here are gravity and electromagnetism, and most simulations, at least, they've gotten a lot better in the last 5 years. But before that, we were focused on dark matter because gravity is easy. It's F equals ma, and it's the simplest version of that. So, but in order to get things right, in order to really understand the active galactic nuclei and the effect they will have, we have to be able to model those. And so there's an additional complication. So I just want to show you on large scales how we've made some progress, not just with dark matter, but also having baryons in simulations. This is a very difficult thing, but Klaus Dolag, again in Germany, has been able to do this. So this is large-scale structure like what we saw last week, scales of many, many megaparsecs on a side in the box. And what you have here is dark matter, its density. You have the gas density evolving, and you have the emission of X-ray temperature from those structures. So this is one small region that will eventually become a cluster. But what's happening here is that for each computation, we're not, even if we knew the theory, we wouldn't be able to recreate an active galactic nucleus whenever it happened. It's just too computationally intensive. There's a lot of physics going on the small scale that would have to be computed simultaneously with the physics at the larger scale. And we're not able to do that yet. So what happens is we create these black boxes, or gray boxes actually, because you don't just pretend they're not there, but you look inside them every once in a while. These gray boxes where you have a simple parameterized theory for what goes in and then how much energy should come out instead of recalculating everything every time. You have an approximation. So we formed our cluster, and it just looks beautiful. Now, if you remember one of my questions from last week, the homework, was to think of these two things that I think are a challenge for cosmology as a science. I mean, it's not an insurmountable one. It's not a challenge to it. It's a challenge for it. And we've been doing pretty well with them over the last 100 years. But there's only one universe, and we can't test anything in the lab, right? All we have is basically archaeological data. So given those two challenges, what other science has the same issue? Feel free to yell out.
Quantum mechanics, psychology.
I heard quantum mechanics, psychology, biology, chemistry. So here's a hint to what I was thinking about. I heard it. Climate. It's very interesting parallel, actually. So, disclaimer, I'm not a climatologist. I met up with a climatologist by accident at a conference in England last year, and I've been thinking about this, but he really sent it home to me how these two fields are really similar, just because of this last point that I made about how they're challenged with simulating on small scales simultaneous with large scales. And I don't know how hurricanes work, I'm sorry, so I won't be able to answer those questions. I did look up how tornadoes work a little bit, but that's not all I know. But to get to the point, the state-of-the-art modeling also requires the same thing of us in climate simulation. So you take a small patch of the world, and you You model it over and over and over again in different ways. You do that simulation by itself in that little cell, and then you come back and you put that back in your larger simulation at a later time. So these things can't happen simultaneously. It's just too computationally intensive. So in space, time, and in energy scales, these distant regions have to interact with each other somehow, and today it's only through these approximations, but we're getting better. So for most of the physics that we've talked about today, we've seen how galaxies form. We've seen how they evolve from bluer to redder, from alive to deader. And we've seen that small-scale processes, disruptive elements, can have a real influence on a system. And these are computationally intensive fields that we must address. And I think if I had another life in science, I might think about climate. Maybe if we can solve the galaxy formation problem, we can then solve the other problem. So then back to the question: what are the applications of everything we've just talked about? I think some people are going to hate my answer, but my answer is the story. The story that we've just told, it has a unique place, at least in my heart. I don't know any other way that we can tell this story, given the wonder on such a scale and such a range of scales that we've probed, and in a scope that few other avenues can really address, I think. From the beginning cosmomicrowave background and the questions of what's before it to actually us sitting here thinking about it today. And that's actually, so that's the answer that my girlfriend gave. I'll read what I remember from paraphrasing it. And she said, and then how utterly baffling it is that we live in a universe itself which we can even begin to understand. Crazy. So maybe Sagan put it better. From his book, from his book Cosmos, he said, if you want to make an apple pie from scratch, you must first create the universe. or sorry, if you want to make an apple pie from scratch. So I think cosmology tells a really unique story, and one that we need to keep telling and refining. And the great thing about this story is that whether you believe it or not, and same thing goes for climate science, whether you believe it or not, it's true. Just because it's complicated and it's hard to understand, it doesn't mean that it's not true. And so I just have one more comment that I want to make before we wrap up here, and that this is, so we've probed our home. We've seen how it's created, how it evolves in time, how it was built. And I don't know if maybe I'm not easily enough satisfied, but this telling of our story and this exploration, I think I would love to see it go on in different ways. And so sort of I'm not sure if I'm going to be the guy who's going to create the warp drive that's going to take us to the next house in the neighborhood, or even into another room in our house. So my hope is that someday we can begin teaching 5-year-olds about quantum mechanics and psychology and biology, and really help them change their intuition, and change their tuition, I guess. And so that they can think about things differently from the beginning. And that's so my selfish wish to go to another part of the universe is to teach a young guy or a young lady how to do quantum mechanics. But that's another story for another time. And safe home. Thanks.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.